the Berkeley Forum. My name is Charlie, and as Vice President of the events for the Berkeley Forum, I'm extremely honored and excited in this moment to officially announce the beginning of our fall 2019 season. Woo!
Yeah!
Of course, we're so lucky to be starting off the season with Dr. Jill Tarter tonight. Dr. Jill Tarter is an astronomer and pioneer in the search for extraterrestrial intelligence and the co-founder and retired director of the SETI Institute. She received her bachelor in engineering in physics with distinction from Cornell and her master's and PhD from UC Berkeley. Where she coined the term brown dwarf. She has spent the majority of her professional career attempting to answer the old human question, are we alone, by searching for evidence of technological civilizations beyond Earth. Here are some fun facts about Dr. Tarter. In 2004, she was named one of the Time 100 most influential people in the world. She has served as the president of the California Academy of Sciences. She has an asteroid named after her. And she was the inspiration for Jodie Foster's character in the 1997 film Contact. So without further ado, please welcome Dr. Jill Tarter to the stage.
All right, are the mics working? Good. Listen, it's a delight to be back here at Cal with all of you, and thank you so much for inviting me to talk to you about something that I'm really excited about. Well, gee, how did that happen? That's my last slide. Excuse me here. Let's go back to where we were. Yeah, technosignatures, right? Oh, maybe I should start by saying a brown dwarf is not some sort of cretin human, it's a star, right? We're too small to burn hydrogen to helium. Has a strange life cycle. So, technosignatures. They're part of what we call astrobiology. And astrobiology is a very young science. And it wonders about the origin, the evolution, the distribution of life in the universe, and it is, in fact, attracting some of the best and the brightest of our students. We're talking about finding habitable worlds through the natural or the deliberate actions of the inhabitants of those worlds. And so there are two branches, if you wish, of astrobiology: biosignatures and technosignatures. So we're looking for microbes and mathematicians. And the mathematicians are my particular favorite. So long ago, Arthur Clarke, who was an inventor and a science fiction writer, good engineer, gave us 3 laws. He said, number 1, when a distinguished but elderly scientist states that something is possible, he, notice the he, is almost certainly right. When he states that something is impossible, he is very probably wrong. Number 2, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And number 3, any sufficiently advanced technology will be indistinguishable from magic. Well, certainly that's the kind of thing that SETI, the Search for Extraterrestrial Intelligence, searching for technosignatures, has been thinking about. We think about the technologies that we know, the physics that we know, and then we interpret it and push it forward into the future, put it on steroids, and wonder how we could find it, right? And that's a good plan. But more recently, a philosopher by the name of Karl Schroeder, an environmental advocate, suggested that any sufficiently advanced technology is indistinguishable from nature, arguing that to be advanced, you'd have to be sustainable, and therefore you would not have these amazing, miraculous engineering structures to be looking for. So who's right? And even if they're indistinguishable from nature, are they really? Is there something that you could still find? So when you think about life beyond Earth, you can discover it. You can find biomarkers, like we find fossils here on Earth. There might be some artifacts. Remember the 2001 artifact on the lunar far side. And perhaps you can find remote biosignatures. That is, you can go to various places in the solar system, planets and moons, and find evidence of either extinct or extant life. You can detect its work product, so you can find technosignatures. Perhaps you can serendipitously use observations made for another reason and in fact stumble over it. And of course you can export it. Like we're talking about going back to the moon, onto Mars, to the asteroids. And there are projects like Breakthrough Starshot or the 100 Years Starship Study or Icarus thinking about how we could actually become interstellar. So SETI is, as I've already said, the search for technosignatures. And we are looking for something that is engineered as opposed to natural, right? Thinking about Karl Schroeder, indistinguishable from nature. Well, what's the difference between natural and engineered to be natural? What kind of things might we find out there with new tools? Maybe some unexpected glimpse because they've orbited big mirrors to geoengineer their world in a way that keeps it temperature the way they want it. The surface temperature of the planet, given its distance from its star, might be wrong in the astronomical sense because it's been engineered to be something other than what it naturally would be. Any advanced technology is going to get rid of hurricanes and extreme weather. It's a good idea. I'm not quite sure how you go looking for that one. And they might have decided that they like things just so, and that icy poles are not to their liking, and so they use a lot of energy to make the temperature of the planet homogeneous in latitude. There might, in fact, be something that looks really strange. Here's the picture that appeared above the fold on the New York Times a couple of years ago. We found this system of exoplanets called TRAPPIST-1. It's a tiny red star, and these planets are all in very close orbit around that star. They would all fit inside the orbit of Mercury. And you have here artist rendering of what those planets look like. We've never seen them. These are artists' imaginations. But when we do get the ability, when we've built the right tools, and we can in fact make images of this system, what would you think if that's what they look like? If they were all the same, because they had been geoengineered. So that's a technosignature. We have around the Earth what we call the geosynchronous belt. We've got lots and lots of satellites doing lots of interesting things up there. Those satellites are pretty much in a plane, right, at a particular distance, and they all stay above the same place on the Earth. If you were a very advanced technology and you had lots of reasons to have things at geosynchronous orbit, you might grow the orbit so that it was no longer a thin plane, but it would grow vertically. Ultimately, we might be able to see that and be able to distinguish it from a natural ring like Saturn's, for example. So that we often refer to that as the Clarke exobelt. You also might end up modifying your star because you want to collect more and more and more energy from your host star. And that might be something that you stumble across as you begin to make stellar observations. So there's also, I thought about a third version of the third law. And that I'm attributing to Nick Bostrom. He actually hasn't said this, but Nick writes about artificial intelligence, superintelligence, runaway, singleton superintelligence. And he might have said any sufficiently advanced technology is indistinguishable from the goal programmed into an insufficiently constrained and boxed superintelligent singleton. What does that mean? Well, suppose you give this superintelligent singleton a goal to build or to make 1 million paperclips. Well, that intelligence is not going to know specifically when they have made 1 million paperclips. It will always be a statistical estimate. And since they'll never really be absolutely sure they've made 1 million, they'll make another 1 million. And they'll make paperclip makers to make more. And so it will turn everything into whatever its ill-conceived goal was. So this sort of uniformity, sometimes called gray goo, might be an artifact that you could detect of sufficiently advanced technology. And so this is generalized artificial intelligence. Where would you look for examples of generalized intelligence out there, artificial intelligence? Well, maybe they've built what we call matryoshka brains. So there's a lot of computing capability orbiting a star for power. The fastest, best computers are in the inner layer, and slightly slower computers run on the waste heat of the layer below them, these matryoshka brains. What would that look like if you were staring through a telescope? They're going to need a lot of power. So you would assume that they're going to be located next to sources of a great deal of energy, such as a black hole or around a pulsar, a neutron star, rotating neutron star. They also might be doing things that we're talking about. There might be lasers that are accelerating sails to take them between the stars. We don't know. We're just thinking out of the box here. What might we stumble across as we begin to observe the universe with better tools? Well, there may be some observable consequences of using different types of energy sources. If they used chemical combustion the way we do, then the James Webb Space Telescope could, with 2 full days of observing, if you could ever get that, detect CF4 and carbon chlorophore fluorides. And that might be essentially, you detect their smog. How about if they use nuclear power? Well, if they use fission, then you have this nasty problem of fissile waste and disposing of it. One clean thing you could do with fissile waste is throw it into your star. And if you did that in sufficient quantities, then you would see enrichment of the rare earth elements, the lanthazides. And indeed, there's a star called Chabelsky's star, where we see exactly that. We see a factor of more than 10 enhancement of praseodymium and neodymium. Astronomers have another explanation, but that is one thing that we've thought of. What about if it's fusion that you're doing? Well, fusion is nasty stuff, and you probably have it in orbit away from population centers. And there's often tritium leakage out of a fusion reactor. Well, tritium is interesting because it has a half-life of only 12.6 years. So you shouldn't see tritium out there except in a supernova explosion, where it's just been manufactured. But tritium actually has a radio emission that's parallel to the very well-known 21 centimeter emission of the hydrogen atom. And if you saw emission at 15, 16 megahertz, that isn't right next to a supernova, you might be very curious what's producing this very short-lived element. So it might be nuclear reactors. Other observable consequences of work, right? They need to generate and store information. They might construct megastructures around their star, Dyson spheres, and if they do enough of it, there might be an old image of the sky that shows a star, and an image years later that doesn't have that star there because it's been encased with something that's absorbing the energy. Something called star tickling, galactic internet, mods that would show up in frequency and time of the stellar spectrum. Or this manufacturing, this enormous replication and uniformity, the gray goo. So there are, in fact, some clouds called Kartolewski clouds, right? not everybody can see them. And so there's a bit of a controversy about whether they're real and near the Lagrange points of the Earth-Sun system. But perhaps those crowds are made out of diaminoid nanobots. Who knows? That might be a technosignature. Transportation, boldly going, right? When there were only a few gamma ray bursts known, a gentleman tried to line them up in four-dimensional actually, space-time to see if they were the acceleration events of a matter-antimatter rocket. Star tickling, if they are an advanced technology, they can produce neutrino factories. They build one and they fly it around a variable star called a SETI variable, which blows up and gets brighter and then dims, and its period is correlated, is closely related to its absolute brightness. But suppose if you have this neutrino factory, the Cepheids puffing up and then getting smaller, and it's not quite ready to expand again yet, but if you zap it with a bunch of neutrinos, perhaps you can get it to expand prematurely. You know what you have? You've got a Morse code that can be seen over the distances between not just the stars, but can be seen to nearby galaxies. We once talked about long, slow ships. Right? So it takes too much energy to go fast. You can have multi-generational, long, slow ships. And they might need to stop off in the asteroid belt to top up the tank or replenish some scarce resource. And so we wondered, well, what would happen if we saw a double asteroid, if we saw something orbiting an asteroid? And we looked and we saw it. And guess what? It's another rock. But it was a good idea at the time. And finally, I mentioned breakthrough starshot, or this idea of building a vast laser system that could accelerate a tiny little postage stamp laboratory with all kinds of different sensors too close to the speed of light. And we could send it to the Proxima Centauri system, where our closest star has an Earth-sized planet. And then faster than light travel, it's there, but I can't deal with it, okay? There's just so many possible ramifications of that. And we're just now talking about photons, electromagnetic radiation, but in fact we understand that we live in a multi-messenger universe. What does that mean? That there are carriers of information that go over vast distances. Electromagnetic waves, light, radio, for sure. Particles of matter, some of them are neutral, some of them are charged. Entangled pairs, quantum mechanics. Gravitational waves, faster than light travel through wormholes or warp drives. And indeed, a gentleman by the name of Hipke has enumerated all of these and told us what's easy, what's hard, at least from our point of view, and what makes sense to look for. And for now, I mean, we're pretty much stuck with electromagnetic waves. And our journey along this path has started back in 1960 with radio telescopes. It now uses optical telescopes. We're pushing down into the near infrared. And we're looking for patterns. We're looking for patterns in frequency and time that we would say are engineered, right? Or sure. So we ask our computers to go find patterns in the noise like this. And there are 9 dimensions that we have to search through. 3 dimensions of space, time, 2 polarizations, frequency, modulation scheme, sensitivity. How sensitive do you have to be successful? And if you take these 9 dimensions and you say that volume of search space is equal to the volume of all the Earth's oceans. Since the first search, now almost 60 years ago, we've sort of covered 1 12-ounce glass out of that ocean. So we haven't done a lot of searching, which is why we probably haven't succeeded, okay? So there's now all kinds of opportunities for improvement. Faster instrumentation, looking for transients, which we haven't done in the past, using AI and neural networks to help us. so that we're not just telling the machine, go look for this pattern, but we're having the machine tell us when there's something that isn't just noise in the data. Data mining, commensal observing, and we're now beginning to have graduate and undergraduate classes, curriculum in this field. So we're training a new generation. And up in Northern California, near Mount Lassen, UC Berkeley and the SETI Institute built a new kind of radio telescope. It's the first time we've built a big telescope out of a large number of small dishes. We do that because a small dish sees a lot of the sky at once. It allows us to do surveys. It allows us to be commensal, to be looking for SETI signals in the same part of the sky that radio astronomers are looking at for their own searches. And we started out by looking for planets, around other stars. We looked at stars that we knew had exoplanets. And then when we learned that the statistics are such that every star has at least one planet, we then switched to look for the nearest 20,000 stars. And those are mostly little red stars. And there's the Kepler field that gave us so many exoplanets. And that place that you don't see any data, that's the geosynchronous belt. We don't look there because we're so noisy, right? The newest 900-pound gorilla, if you wish, is the Breakthrough Listen project that's run out of the Berkeley SETI Research Center. $10 million pledged by Uri Miller over 10 years. They're looking at the quiet part of the radio spectrum. They're looking at 1 million stars, 100 galaxies. They're looking in the ecliptic plane. That's the plane in which the Earth orbits, because anybody living out there would see the Earth in transit against our own sun. And they'd know we were here. And they're looking at exotic objects. So far they've built wonderful detection instruments for this telescope, the Green Bank, West Virginia 100-meter telescope. This is the 64-meter telescope in Parkes in New South Wales, Australia. They've also got instrumentation on the Planet Finding Telescope at Lick Observatory down near San Jose. And they have made deals with the FAST telescope in China, with the Merlin Array in South Africa, and with the Lovell telescope in the UK. And we'll be building instrumentation for those telescopes as well. And then there's also Breakthrough Watch, which has upgraded the instrumentation on a very large telescope down in Chile. And it will be looking to image planets around Alpha Centauri A and B. There's more. How many of you have SETI at home on your computers? Some of you? Good. Well, the rest of you can do it as well. It's a program that runs in the background and analyzes the data that has been recorded at Arecibo Observatory for the same kinds of signals that Breakthrough Listen and the SETI Institute are looking for. Here's a low-frequency array in the Netherlands and Europe that's looking for transients. This is a telescope that an Italian group uses occasionally. This is a sky survey being run by students just outside the Deep Space Network in Goldstone, California. Here's another array in Malura in Western Australia being used. And in optical frequencies, the students at Harvard have built a sky survey telescope. We reanalyze all the data that's taken at Keck to find planets using radio velocity techniques, and we're looking for lasers. There's a amateur astronomy optical SETI telescope in Panama. We're looking at data from surveys of the sky at various frequencies, looking for Dyson spheres and those marvelous engineering miracles. And then in the near future, we're going to be putting a couple more SETI-specific telescopes on the air. First of all, we're starting with Veritas, which was built to find high-energy cosmic rays. And we've tweaked the software so that instead of finding big trails of detections across the sky from Cherenkov radiation, they look for the same pixel lighting up in each of the 4 telescopes. That's just come on the air this spring. PanaSETI is an optical all-sky survey, and Laser SETI, another optical all-sky survey. So PanaSETI, if any of you walk around the Berkeley Hills and see the Buckminster-Fuller geodesic domes that are up there, that's the idea. You fill those domes, you cover them with a big plastic Fresnel lens. You focus a big area of the sky onto a tiny detector, and then you tile 10,000 square degrees on the sky. And you build 2 of them because if you're looking for transients, you want to have verification that it was not just a mechanical glitch. And laser SETI is also looking for bright flashes of light. It uses cameras rather than the telescope and lenses of panel SETI. And with 8 cameras at each of 6 sites around the world, you will see the whole sky. And if you have 12 sites, then you have, again, the possibility of confirming a transient detection and being able to observe through most weather. So we're looking at 12 sites around the sky for those cameras. The astronomers are building wonderful new instruments. JWST, we hope, will finally launch. And then the decadal review of astronomy and astrophysics will tell us whether we launch W first or HabEx or LUVOIR. These big telescopes in space are what you need to image the exoplanets and examine their atmospheres for the biosignatures. Here's a weird telescope. It's more like a radio interferometer than an optical telescope. Actually, it's more like a Ferris wheel, right? But for the nearest planet, right? For Proxima b, if there was anybody living there, we could deconstruct the light curves from many years of observing to tell you about that. Other telescopes, the TMT, to be built somewhere in the world, the 30-meter telescope, the GMT in Chile, the European Extremely Large Telescope, that's 39 meters. It's downsized from the overwhelmingly large 100-meter telescope we couldn't figure out how to build, but we are building a 40-meter telescope. And then the Large Synoptic Sky Survey, which will give you a new picture of the sky every 3 days and show you things that are changing on the sky. We have panel SETI and laser SETI, FAST, the Chinese telescope, and eventually the Square Kilometer Array in South Africa for radio. And if we're lucky, the next generation VLA here in the United States, and then Colossus. If we can make that Life Finder telescope work, this is an exaggeration or an elaboration of it that could actually find the heat signatures of distant extraterrestrial cities, right? So the fantastic thing about SETI, and the reason I like to talk to people about it, is I make you think bigger than when you came into this room. And it's as if I'm holding up a mirror to all of you and saying, see, all of you in that mirror, you're all the same when compared to something else that evolved elsewhere. So this whole idea of SETI gives us a cosmic perspective, which helps to trivialize the differences among humans and may be very important for our very long future. So the last thing to think about is time. If SETI is ever going to succeed, 2 technological civilizations have to be close enough in space and close enough in time. They have to last long enough to be co-aligned, co-eval in the 10 billion year history of our galaxy. So if SETI succeeds, we will know that it's possible to have a long future. And so the last word is due to Caleb Scharf at Columbia. On a finite world, a cosmic perspective isn't a luxury, it's a necessity. Thank you.
Awesome. Well, thanks so much for that address, Dr. Tarter. Every Berkeley Forum event has a moderated question and answer portion with one of our trained student moderators, and tonight it is Oriana Ja. Please welcome her to the stage.
Thank you for coming to speak with us tonight.
It's my pleasure.
It's a pleasure to have you. So I'd like to begin by asking you about your SETI-specific work. SETI has received a lot of cultural attention in its past, especially on the internet and in science fiction. Given this context, how do you maintain the scientific rigor when communicating about the science of SETI to the public?
Well, scientific rigor is an absolute necessity, and one of the first things that we did when we were getting this field started is we went to great lengths to distinguish ourselves, to distance ourselves from all of the UFOs and all of the nonsense that's out there. And if we ever claim a signal detection, we better be willing to show you some extraordinary proof. And that's what's lacking in these other fields of pseudoscience. So we will not claim a detection unless there is just overwhelming evidence that what we found is what we think it is. And if we don't understand what it is, we'll announce it just that way with lots of caveats. So particularly with respect to biosignatures, looking at the chemical structure of the atmospheres of distant exoplanets, we'd like to find chemical disequilibrium. We'd like to find oxygen and methane together. That's what our atmosphere looks like, and it's because of biology on the surface. But there are other ways of making oxygen, other ways of making methane that don't require biology. And so when we make these announcements, we're going to have to be very clear about what it is we found, what the evidence for it is. And anybody should be able to follow up and verify or nullify our detection.
Given the variety of explanations that you've mentioned that can be used to explain natural phenomena, how do you interpret Schroeder's version of the third law, where if alien technology is in fact indistinguishable from nature, how does this change the scientific approach used to seek out this technology in comparison with the past?
Right. So we were going gung-ho for engineered signals. And now we need to think about how a world might not have these huge structures or have obviously engineered features, but might subtly be different. Like, as I showed the picture of the TRAPPIST-1 system, each of those planets should be at a different temperature because they're at a different distance from their star. But if we find that they look like a normal planet, there's no great flashing signs that say, engineering here, right? They just look like a normal planet, but they're the wrong temperature, or they're all the same temperature. That isn't going to happen naturally. That takes the use of a lot of energy to change things. So we might be looking for subtle things like that. We can't ever promise that we're looking for the right thing. We in fact know that perhaps we're doing a spectacular job and looking for exactly the wrong thing. And there's some technology we haven't invented yet that we should be using, or there's some interpretation of observations that will be made for astronomical purposes that we could use to infer someone else's technology or modification of their own work.
So you've spoken at length about looking for the subtle changes. How or what has, if anything, has caused the shift in the scientific assumptions about the nature of advanced technology?
Well, we always reserve the right to get smarter, right? And it's thinking about the instruments that are coming down the pipe. I mean, you build a 40-meter telescope on the ground, or you build a 15-meter telescope in space, and you're going to be able to see things that we've never been able to see before. And with that in mind, the fact that we're going to finally image these planets that we're finding, thinking about what those tools will allow us to do has caused us to sort of stretch our minds and try and conceive of different ways that we might detect someone else's technology.
Earlier today, it was announced that the ATA is actually going to be expanded. What do you think?
I hope it's going to be expanded, but that means somebody has to give me a check.
Right.
It's going to be improved.
So, given the perhaps increase in funding for the project, how do you think this bodes for scientists or the public or anybody essentially who says that we should focus on short-term projects that have more tangible results rather than looking longitudinally?
Well, I tried to address that at the end by saying that if by giving talks, if by doing SETI and getting people excited about SETI, we can cause them to take on this bigger perspective, this cosmic perspective, you know, to see themselves as all the same. I think that really bodes well for a long future, okay? And I think it's important. We have all these challenges on this planet, and they're challenges that don't respect national boundaries. We're going to have to work on global solutions to them. And one of the best ways to start that process is to begin seeing ourselves as Earthlings as opposed to Americans. And so I usually give a homework assignment, right? So we're in a class, I'll do it with you. So when you get back to your devices, why don't you go in to all your profiles and change the first thing that you say about yourself to be that you're an Earthling. And then even better, start acting like it, right? I think this cosmic perspective is incredibly important.
In terms of that philosophical question, or that philosophical idea that we are all Earthlings, you've previously said that the ultimate purpose of finding extraterrestrial life is driving home the realization that we are all, quote, the products of a billion-year lineage of wandering stardust. What do you think are the consequences or effects that this realization will bring?
Well, again, if we can, because we have something to compare ourselves to, because we can really see that what we think is correct, that biology is just the natural outcome of physics and chemistry in the right conditions, that I think seeing ourselves as one among many, because of course in physics you count 1 to infinity. When you have only one sample, it could be unique. The moment you find the second one, you know there are many. So finding life somewhere else will tell us that life is ubiquitous out there. And seeing ourselves, again, in that light, I think it makes many of our problems look pretty trivial and insignificant. I think that, yeah, if I could spread a meme, it would be Earthling. And I think that's what we need to do.
All right. For the sake of time, this will be my last question before we move on to questions from the audience. As you mentioned earlier in your presentation, the amount of galactic observations done by SETI initiatives can be compared to a cup of water in all the world's oceans. In your view, how could scientists more effectively, or most effectively, expand the search to see more of that ocean?
Right. Well, we're doing that exponentially right now. The computing is getting so much better. We're finding ways to build different kinds of telescopes. We've had, up until now, very, very limited sensitivity to transients. If there's a signal out there, either in optical wavelengths or radio wavelengths, it has to persist so that we can verify it, right? We just, if it goes blink in the night once, we're very unlikely to believe that it's real. So the ability to open up the transient space, sensitivity to that. We may have had these signals all along and we've just written them off as some experimental glitch. Using artificial intelligence. So again, we're not telling the computer, look here and see if you see a straight line. We're being able to, in a far more general way, have the computer look at the data and tell us whether there's something that is other than noise of any kind in that data. Those are two paths that we haven't been able to follow yet. And of course, you know, there are always the zeta rays that we haven't figured out yet. But when we do, I think we should use those too.
Great. Thank you so much for answering all of my questions. We're now going to be moving on to audience questions. If you have something you'd like to ask Dr. Tarter, please raise your hand and I will call on you. Just give me a moment to get through this. When I do, please remember to speak up and keep your questions concise.
So why is the emphasis of most Earth investigations for astrobiology focused on intelligent life when there's probably so much more primitive or before establishing life that don't exist even in our own solar system, such as geothermal vents on the slugs.
Right. And I think I didn't say that it was all about looking for intelligent life. I said that's what I was interested in. So astrobiology, this big umbrella, has these two disciplines under it. And let me tell you, the funding for looking for biosignatures, for microbial life, any kind of evidence for life, is much, much greater than any funding for SETI. It's just my passion is for the mathematicians. The microbes are well represented with the rest of the scientific community. I think we're doing a good job there.
Either one of you three.
So how do we account for anthropocentric biases that might affect what we're looking for? Because couldn't there be life that's equally as intelligent, or if not more than us, that just doesn't prioritize technological progress or space exploration?
Absolutely could be. We call it SETI, the Search for Extraterrestrial Intelligence, but we don't know how to define intelligence, right? We don't know how to find it at a distance. So what we've been doing is using technology as a proxy for intelligence, because technology is perhaps something that we could detect over vast interstellar distances. Is that the only thing that could be there? Absolutely not. But you know, a planet that is full of poetry writing and singing dolphins and whales, I'm not going to be able to detect. They're not modifying their environment in ways that are being able to be sensed over vast distances.
So a lot of the technology that you talked about seems to be like a lot far past where current human technology is. And assuming that these civilizations exist, wouldn't it be easier for them to notice us than for us to notice them, seeing as they have more advanced technology? And if they haven't reached out to us or contacted us, is that maybe like an implication that we wouldn't have the ability to contact them if we were to find them?
Yes, that's a good question. I'm postulating a lot more capability for this advanced technology because it makes it easier for us to find. And they, particularly, I mentioned that the Breakthrough Listen project will be scanning what we call the ecliptic plane, a plane in which the Earth orbits. Particularly, we want to look there because anybody who also lives in that plane will see the Earth transit in front of the sun. They'll know we're here, and that might be a reason for them to select us as a target for whatever technology they're transmitting. And then people say, well, if they're so advanced, then why aren't they here? Right? If they know about us, why haven't they come? And then you get into the question of whether or not interstellar travel is ever viable or defensible or something that someone will decide to do. And yeah, if they have better technology than we do, then they have an easier time finding us than we have finding them. That's it. I mean, I can sit on the lawn out there and wait and twiddle my thumbs and wait for them to come here, but I'm too impatient. I want an answer to this question, so what can we do?
So if, say tomorrow, you did find a confirmable sample, or like, what would be like the first thing you would do other than like be really stoked?
Yeah, we've had that experience. We've had some false positives, and the adrenaline is just unimaginable. So what would we do? We try and use all the equipment that we have at the discovery site and make sure that it's what we think it is. We would get an independent confirmation because we worry about hoaxes from smart Berkeley students, right? So you want to get somebody else to be able to see it with equipment that we didn't build and software we didn't write. Then you use what's called the IAU telegram system, and you alert all the world's observatories to the discovery and make sure that they get the discovery information. You do that, A, because they have some other tools that you don't have, and then they might want to look in a different way. But you also do that for another reason. Then you are, in fact, educating a whole cadre of scientists around the world about the facts of the discovery, so that when their local media person tries to write an article, they don't have to make it up. These scientists can help interpret for them what was actually found. And then, of course, the last thing you do is you tell the world, because the signal, if it's there, or the observation that's been made, isn't for the benefit of California or the United States. It's the property of all humankind, and everyone needs to be able to react to it as they want. So we tell the world.
I was just going to ask, how do you remain optimistic in a field where you don't really know when or if you're going to find the result you're looking for?
Yeah. Well, it helps to be born optimistic. It also helps to be stubborn as hell. It helps to have been the only female in a class of 300 engineering students. That in fact toughens you up. And the other thing is, you don't get out of bed every morning saying, yeah, today I'm going to give the signal today, right? You're going to go to bed disappointed more than not likely. So what you do is you get out of bed in the morning and say, I'm going to figure out a way to do the search today better than I did it yesterday. What new tools? What new way of looking? How can I reprogram my search strategy to do a better job? And then incrementally, it's very satisfying.
This will be the last audience question.
I'm curious, if, so say, assume the best case scenario and you discover intelligent life fairly soon, but it's very far away, what's the sort of procedure there to go about establishing contact? I mean, say it's 100 light years, and we take 100 years for any sort of information from us to reach them, and vice versa. How do we know that they received it and understood it?
Right, yeah. For that very reason, the sort of tyranny of light speed, Phil Morrison, one of the founders of this scientific discipline, has called SETI the archaeology of our future. So if there's a signal and there's information content, it's going to have traveled a long way. So we'll be learning about their past. But the very fact of success means that on average, technological civilizations have to last for a long time. Otherwise, there would never be two civilizations lined up in the 10 billion year history of our galaxy to detect one another. So even if there's no information content, we still learn that it's in fact possible for us to have a long future. Somebody else made it through, Dana, and therefore we can too.
All right, well, I think that's all the time we have tonight. Thank you again for answering all of our questions, Dr. Jill Tarter. And now I'd like to invite our VP of Events back to the stage. Take it away.
Awesome. Well, we want to say thank you so much for coming out tonight. And as is the case with every Berkeley former event, we'd like to present you with an official framed poster for this.
Great. Oh, thank you.
Let's get started. So much for coming out tonight. If you weren't able to get a flyer out front on our registration table, please check out our lineup for this semester online on our Facebook page or at berkeleyforum.org. And also, if you could take a quick minute to go to tinyurl.com/berkeleyforumfeedback and give us your thoughts on this event, we'd really appreciate it. So thank you so much for coming out tonight.